Now, what does the semiconductor industry look like today? Now, almost all of the world's most cutting-edge chips, this one's currently using what the marketers call the 3 nanometer process with the extreme ultraviolet, are made by one company, TSMC, in Taiwan. These are the chips used in flagship smartphones, for example an iPhone, and for AI, the H100 GPUs that are used for most training compute for AI. Now, TSMC is not exactly a household name for most people. People tend to think of like Apple or Google or something like that, but Apple or Google all rely on these chips made by TSMC. TSMC basically follows the foundry model. They figured out that manufacturing chips is so complicated and so expensive that you should just focus just on that. Don't worry about designing them, don't worry about marketing, don't worry about putting them in smartphones or AI systems. They have a company that's going to focus 100% on how you make these bits of silicon. And then offer your services to anyone in the world. So anyone in the world can say, yes, I'd like to make a chip, or here's a design, build it for me. Because anyone in the world can use it, you get enough customers that you can spread the incredible costs of building the fabs and researching the new technologies over all these customers, and so undercut it. In the past, most companies would both design the microprocessors and build them. For example, Intel would design the microprocessors and make them. Samsung still does this. So a Samsung phone will often have a Samsung microprocessor designed and built by Samsung in a Samsung phone. But increasingly, most high-tech companies are fabulous. They don't make their own silicon chips, they design them. Examples would be Apple, Nvidia, and Qualcomm. Nvidia makes most of the high-end artificial intelligence GPUs. Qualcomm makes the chips that allow things to communicate via Wi-Fi or mobile communications. But these companies will design the chip and then pass them on typically to TSMC or a couple of other foundry companies around the world who will actually build them. Now that's for the cutting edge chip. These are the ones using extreme ultraviolet. The less advanced ones, the ones that are 4 or 5 generations behind, are still very useful. These are the ones that are used in most cars or toothbrushes or credit cards, and they're made by many companies in many parts of the world. But the really bleeding edge, cutting edge ones, almost all made by 2 or 3 companies: Samsung, Intel, TSMC, SMIC, and mostly TSMC for the really, really cutting-edge ones. And that's a bit scary. That one company is responsible for an entire industry that's 40% of the world. But it's not even just one country and one company. It's much more interdependent. While TSMC makes most of the cutting-edge chips, they don't make the equipment to do it. For example, the extreme ultraviolet lithography we've talked about, this uses machines and there's only one manufacturer in the world that makes these machines. So TSMC has to buy these machines from this one manufacturer. And that one manufacturer is a company called ASML. Seem to be talking about a lot of 4-letter acronyms here. ASML is in the Netherlands. They make the only machines in the world that can do this extreme ultraviolet lithography. Each of their machines costs about $300 million. And so TSMC, Samsung, Intel, they have to buy these machines. But you can look at ASML. They are the only company in the world that makes these machines, but most of the components that go into these machines are made by other companies. So, for example, the lasers come from a German company, Trumpf, and the mirrors from another German company, Zeiss. And so when you look at actually what goes into making one of these cutting-edge silicon chips, it's sort of being spread all over the world. You have to design them. How do you locate where you're going to put 90 billion transistors to make it show a YouTube video to you? This is mostly done by a small number of American software companies that write the incredibly complicated software designed to turn what you want to do into a design in silicon that can then be sent to TSMC to manufacture. There are all the chemicals. You need all sorts of very specialist chemicals, ultra pure silicon, the photoresists, the things that etch, the things that dope. Each of these are made by maybe 1, 2, 3 companies somewhere in Japan or Korea or the US or somewhere in Europe. And so it's a totally woven, interconnected system. No one country, not even Taiwan, can actually make silicon chips by itself. It needs most of the world to do it. famous example fairly recently is that there was a fire at one small company in Japan. It turned out they made almost all the photoresist. This is the thing you lay on top of your thing that exposed it to the light and etched it away. They made most of the chemicals photoresist for the world. Due to their fire, silicon chip production around the world was shutting down. And so this means there's a lot of single points of failure. It's a very fragile system. It could very easily go wrong. What happens if there's an earthquake in Taiwan? Or, of course, the government of mainland China, the People's Republic, has claimed the right to invade Taiwan and bring it back into the motherland by force. That would certainly take out the Taiwanese semiconductor industry. In fact, the government of Taiwan sees its semiconductor industry as its silicon shield. They think that by dominating the world production of the silicon chips, that makes them so important that other countries will fight to defend them from China, should China choose to invade. But of course, TSMC can't do these things without ASML's extreme ultraviolet lithography machines. What happens if ASML goes bankrupt? It's very dangerous being in this business. You might be at the cutting edge right now, but what's the cutting edge going to be 4, 5, 6, 10 years in the future? You have to be investing billions of dollars now in the research that's going to allow you in 5 or 10 years to make chips that are another 20 or 30 times smaller. You can easily guess wrong. People often will guess, where do we think the technology is going? What do we invest in now? If you guess wrong, you can go bankrupt. So ASML might not exist in 5 years' time. They might have bet too much money on technology that doesn't work. So it's very risky. As a result, there's a lot of geopolitical tension. Bear in mind that these silicon chips are needed for almost all war fighting. We've seen in Ukraine drone warfare, guided cruise missiles, ballistic missiles. They all require huge numbers of very advanced chips, and AI is only going to make that worse. So a lot of countries are trying to say, we need a semiconductor industry, we need to be involved in this. Many countries have tried, some have succeeded, and many have failed. Australia, for example, in the 60s and 70s had a big push to become involved in silicon manufacture. Failed. UK likewise, France likewise. The USSR, Russia, they had a huge research investment actually in spying. They would steal almost all the secrets from the US semiconductor industry and then try and recreate it. They had built a whole city, Leningrad, which was full of semiconductor scientists, a secret city, very pleasant conditions. They got all their best scientists in one place to build silicon chips. They supplied them with all the stolen secrets from the US. They still couldn't get it to work. That was a large part of the end of the Cold War. They realized they couldn't keep up with the American high-tech equipment in the military. But it is possible. Japan in the 60s and 70s managed to corner most of the market for memory chips, DRAM chips, dynamic random access memory. Then South Korea in the 80s and 90s managed to pinch most of the industry from the Japanese. And of course Taiwan in the 1990s and 2000s. And right now China is investing huge amounts of money in trying to build its own domestic industry while labouring under sanctions from much of the rest of the world. How can this succeed? Why does it often fail? Well, there are some common features that make it succeed. One is massive, like tens or hundreds of billions of dollars investment over decades. This is where Australia went wrong. The investment was far too small and it kept changing. Every time a new government came in, the policy changed. So you need a consistent policy over a large period of time and you need a lot of money. You also shouldn't try and go it alone. You should integrate into supply chains. Don't try and do everything. No country does everything. You might buy your equipment from one place. Just pick one place in the supply chain where you can add value. Becoming a researcher in this field, this is the biggest employer of physicists in the world, but you don't just study a course in semiconductors and then go and build them. You learn on the job. This is very much a master-apprentice model. People learn by doing, so you need to get a job with one of these companies and work there for years. And all the new companies that have succeeded have poached people from existing companies. For example, TSMC, Morris Chang, the founder of that, had worked for many years building semiconductors for Texas Instruments. He was passed over for the job of director and decided to move to Taiwan and set their new company up. The research is very specialized. As I said, it's a master apprentice. You don't do a PhD and then be able to build semiconductors. You do a PhD, then you'll be tens of thousands of people with PhDs working in these companies and then work for years. So there's a real amount of trial and error. People have to get the yield up. It's very easy to have a few percent too low a chance of success in each of the 800 steps that build the semiconductor. It all goes wrong. So people could spend their entire lives How do we get this ion beam to make things slightly more reliable so we can get the yield up from 10% to 20%? Or how do we etch things or polish things or check them, meter them? People become very specialized. You could spend your entire career working on best ways to strip photoresists or best ways to improve layers on extreme ultraviolet mirrors or whatever it might be, new fans for lasers. Companies are very secretive. Most of the information about how this works is not in the public domain. You can't research, go to the library and look up papers. Obscure details can be vital. Intel had a policy of copy exactly. It could be that people think they built one fab and after 10 years of trial and error they get the yield up to 50%, which is pretty damn good for these things. Then they try and build another one next door. It's not working as well. It turns out someone used a different paint, and the different paint leaked a different chemical into the atmosphere. Maybe the pipes were made of a different type of plastic, and new polymers are breaking off and flowing to form more dust. Every detail matters. You need to be incredibly persnickety, very, very careful. Look at every single microscopic detail, because you get anything wrong, the thing can fall to pieces. And even if you've got all that, you've got the very careful people who've worked before, you've got the billions of dollars investment over centuries, decades, it's still very hard. You need an edge. Why should people put their semiconductor plants in your country when there are plenty of other countries fighting for the business? So you need some edge why they might want to come to you to begin with. And for Japan to begin with, it was a combination of cheap wages. Japanese workers were paid much less than American workers back in the 60s, and also a government that would steamroll the bureaucracy. If you had to build in California but you needed to get permits from 100 different states to build your factory, all of which is going to take you 5 years, and Japan would just wave it through and do it right away, you go to Japan. Cheap finance in Japan or Korea, the government would lean on the banks to give you money at low interest rates. Interest rates are crucial because you have to spend so much money up front and then you get the proceeds later. If you're paying interest the whole time, that can send you bankrupt. So having a government that will give you cheap financing can help. No unions, highly trained workforce that's prepared to work long hours for not much pay. Maybe cheap electricity. Nowadays, the amount of electricity or pure water you need is so high that a country where the electricity price is cheap might be the place you go. You need some sort of advantage like this. This is what's happening right now around the world. China has invested well over $100 billion over many years, and they can't quite make the cutting edge chips, but they're maybe a generation or two behind, but possibly catching up. The US is currently trying to bring chip manufacture back. Many of the components that go into chips, like the software and some of the machines used, are built in the US, but the final assembly is generally not done in the US for the really cutting edge chips. But President Biden tried a carrots approach to bring it back, huge subsidies, the so-called CHIPS Act, which worked to some extent. The current President Trump, at the time of writing this, is using a sticks approach. If you don't build in America, we will hit you with massive tariffs. And some combination is causing, for example, TSMC are building a fab in Arizona, and other companies are trying to build fabs in the US. It's more expensive in the US, but if you get large subsidies or you get hit with penalties if you don't do it, it's tricky. The tariffs are a bit counterproductive because even if you're building a fab, you'll still need to import your extreme ultraviolet machine from the Netherlands and your photoresist from Japan. If you're paying tariffs on all those, it still makes things more expensive. There's a fascinating article about the problems that the Taiwan company TSMC had trying to build their fab in Arizona. There was a huge culture clash between the Taiwanese staff and the American staff. The Taiwanese reported the US workers were lazy, didn't follow instructions, wanted to be coddled, not dedicated enough. If something broke at 2 in the morning, they wouldn't get out of bed. The US workers felt they cannot have a work-life balance working for this company where long hours are expected, and they're forced to follow often pointless instructions just because someone up the chain told them what to do, even though it's totally stupid and was a waste of their time, and they knew it was a waste of time, they still had to do it. So it's been a real battle, but this is the geopolitics that's going on at the moment.